All right, good morning, chemists. We'll get started now. We probably won't quite finish chapter 16 today, and so that probably means we will not have homework due on Monday, so you can focus on your midterm in recitation tomorrow. All right, but we still have to continue on with chapter 16 in preparations for midterm 13. So we're going to dive deeper into acids and bases, specifically weak acids and weak bases and their conjugates. So this is where things get kind of iffy. But if you continue to ask yourself, what am I looking at? Am I looking at a weak acid or am I looking at its conjugate? A conjugate of a weak acid is a what? Weak base. So if we have a weak base, then we have to be using Kb. All right, versus if, are you working with a weak base like ammonia, or are you working with its conjugate acid, ammonium plus, NH4 plus? And so constantly looking at the chemical formula and recognizing, am I working with the base or the conjugate acid form, tells you which Ka or Kb to use there. So we're going to dive deeper into, okay, what are we looking at? Are we looking at an acid or a base? And we're going to practice these skills by just looking at a formula to tell, okay, is something going to be acidic or basic when you dissolve it in water? All right, so conjugates. Typically when we think of like an acid or a base, like the generic ones, HA is an acid. B is a base. Those are neutral species. But once we make their conjugates, what's the conjugate base of HA, the acid? A minus. See how that's an anion? Versus what's the conjugate of the base B? HB plus. See how that's a cation? All right, so what we're going to see when we form these salts is if we inspect the salt, notice that the cation part of the salt, remember how we name salts, it's always cation then anion when we name it. If you look at the cation, typically these are acids because they're the conjugate acid of bases. All right, so cations, if you're going to have an acid, is going to be in the cation slot. All right, so examples would be, again, the conjugate of a weak base, so like ammonium here, or Lewis acids. I should do a different color. Lewis acids, different color, come on. All right, so some examples of Lewis acids are very highly charged cations. Typically, these are transition metals. All right, and we'll look deeper into this in a moment. So basically, in the cation slot, if you're going to find an acid, it's going to be in the cation slot. Look for conjugates of weak bases, so like ammonium, like ethyl ammonium or something like that, or you want to look for highly charged cations, Lewis acids, so like iron 3+, aluminum 3+, what else is there? Yeah, those are two of them, all right? What you also might see in the cation slot is common group 1 or 2 metals, so like sodium plus, calcium plus, potassium plus. So those cations, those are not charge neutral, they are pH neutral salts. The reason that they are pH neutral salts is because these group 1A and 2A metals, they are actually conjugates of strong bases. All right, so the conjugate of something that's strong, if something's really strong, its conjugate is really what? Weak. So if you have a strong acid, its conjugate is so weak that it's pH neutral. So sodium plus, potassium plus, all of those things, if you have that in water, they're pH neutral, so you essentially can ignore it in trying to determine whether the salt is overall acidic or basic. All right, so those are the things that you want to look at. So like sodium plus, potassium plus, those are pH 7. For the most part, we're at 25 degrees Celsius, so they're pH neutral. All right, so those are the cations. Those typically are where your acids show up. Versus anions, these are typically where your bases show up. Why bases? Again, because when we thought about making conjugates, the conjugate of a weak acid is a weak base, and it's an anion. So if you're going to find a base, it's going to show up in the anion spot. So that anion will be a weak base if it's the conjugate of a weak acid. So you want to look for things like carbonate, acetate, fluoride, because all of those are anions that you use to make a weak acid. Hydrofluoric acid, acetic acid, what's the other one I said? Carbonic acid. So those are 3 weak acids. Their conjugates are weak bases. So that's what you want to look for. All right. And then finally, anions, you know, if the conjugate of a weak acid is a weak base, then the whole salt, if you dissolve it in water, will be basic. We also have some pH neutral anions as well, and it follows the same scheme. HCl is a strong acid, so it's really, really strong. So the conjugate of HCl is not an acid at all, right? That it's pH neutral. So these pH 7 anions, these are conjugates of strong acids. So remember those 7 strong acids? So they're going to be like chloride, nitrate, chlorate, perchlorate, all of these anions, if you put those anions in water, they will be pH 7. They'll be charge neutral because they're the conjugate of a strong acid, so they are really crappy bases, so crappy that they just do nothing to water. They are pH neutral. So that's what we want to look for here when we're given a formula. Can we predict, is it acidic, basic, or pH neutral? Yeah. No, so it's the language is the stronger the acid, the weaker its conjugate base. The stronger the acid, the weaker its conjugate base. So if you have something that's so strong, its conjugate is going to be so weak that it's not even going to be a base at all. Versus if you have a very weak acid, its conjugate is going to be a fairly good base. So do you see that relationship there? So a strong acid has a really crappy base. It's so crappy that it's not even a base at all. It's pH neutral. Does that make sense? Okay, all right. All right, so are we going to practice it on the next slide? Nope, not yet. So let me explain why. So the new thing here is another class of acids would be Lewis acids that fall in the cation place here. And this is why things like iron 3+, aluminum 3+, these ions, these cations, are actually slightly acidic when you put them into water. So let's remind ourselves about Lewis acids and bases. Lewis acids and bases, that theory inspects what about a reaction? It inspects the electron or proton? Electrons, all right. So Lewis acid-base theory, you need to reference yourself to how are electrons moving in a reaction. So a Lewis acid is an electron acceptor versus a Lewis base would be a what? An electron donor. All right. So let's think about it. Iron 3+ is a cation. So think about it. How do you make a cation? You remove electrons from it. All right. So if you're removing electrons from a cation, it makes sense that electrons on something else can come in and swoop in and make a chemical bond because that cation lacks electrons. It's going to be much more likely to be an electron acceptor because it's positively charged versus something that has like a lot of lone pairs or is negatively charged is more likely to be a Lewis base because it has extra electrons to donate. And so that's why we see a lot of these cations here, and you see a lot of these are like transition metals. Not our group 1A or 2A metals because those are pH neutral, but these ones actually are slightly acidic. They're positively charged. They attract, you can think they attract electrons, therefore they're electron acceptors, they can act as Lewis acids. All right, and so you can see that here's a bunch of Ka values for these Lewis acids. All right, for like iron 2+, iron 3+, all that stuff. So they're different values. Some of them have different acidity and basicity, different degrees of acidity. Sorry, they're not basic. And so the trends are, these don't really, these actual numbers don't need to be memorized, but what we can see and draw from this chart is that the acidity, or basically the magnitude of Ka, increases with increasing charge. So for example, like a +2 ion versus a +3 ion, Think about it. Which one attracts electrons more, +2 or +3? +3. And so the +3 is going to be more acidic because it can attract more electrons. It can act more like a Lewis acid, which is an electron acceptor. And also as size decreases, so smaller cations typically are better acids because it's highly, has a high charge density and again can attract electrons much more and act as a Lewis acid. All right, so why these things when you put them into water, the reason these cations form acidic solutions is because the cation is the Lewis acid, it's the electron acceptor. And when you put it into water, water is acting as the Lewis base. But let's look at the structure of water, all right? Let's look at the structure of water. Does it make sense why water would be the Lewis base versus like iron 3+ would be the Lewis acid? What part of water makes it the Lewis base? What is a Lewis base? It's something that donates electrons. So is there something obvious on water that makes it look like a Lewis base? What is it on it? It's the lone pairs on it. Yes, the lone pairs on it, on that water molecule right here, give water the ability to work as a Lewis base that can then attract itself and form a chemical bond with iron. So we see water is the electron donor, so it's the Lewis base, and iron 3+ is the electron acceptor, it's the Lewis acid, right? So that's kind of reviewing of Lewis acid base theory. Okay, so let's put it all together and look at some salts and predict whether this salt, when you put it into water, is the solution going to be acidic, basic, or neutral? All right? So here's the strategy. Here's a bunch of salts. We're going to work through them one at a time. Since they're salts, they contain a cation and an anion. So our strategy is first separate and look at the cation and anion separately and look at them one at a time. So ammonium nitrate, if like this was chapter 4, right, and we were doing net ionic equations, this would separate into what ions? Ammonium nitrate. You would get a what and a what? You would get a NH4+, and what else do you get? Nitrate. That's it, right? So that's like chapter 4. If you place that in water, it separates into its ions. Those are the two things you get. Right? So now we inspect them separately, and you ask yourself, am I looking at an acid or a base? But the hard part here is that we're not looking at HA and B, we're actually looking at conjugates. So NH4+ is a what? It's an acid. How do you know it's an acid? How do you know it's an acid? So this is an acid. The reason it's an acid is because it is the conjugate of ammonia, which is a weak base. So its conjugate is also going to be a weak acid, all right? So ammonium is going to be acidic versus nitrate. What about nitrate? What is that going to be? Acidic, basic, or neutral? It might look basic because it's the anion, but let's think about it. Nitrate is the conjugate of what acid? What's its conjugate? So how do you make a conjugate? You either add or remove a proton. So we're going to add a proton back to that nitrate, and what do we get? We get HNO3. What kind of acid is that? This is a strong acid. So if this is a strong acid, if nitric acid is a strong acid, what does that make nitrate? pH neutral. It makes it pH neutral. So this is, I'll just say pH 7. So nitrate is pH 7. So what do you think will happen if we combine, if we put into water a substance that is pH neutral and something that is acidic? What will happen to the overall solution? It will become acidic. Yes, that's it. All right. So this whole thing will be acidic. Right? So what we're doing is we're looking at the cations and anions, undoing the conjugates, and identifying, do these conjugates come from weak things or do they come from strong things? And then that will help us decide whether the cation or anion is a weak acid or weak base. Okay, let's do the next one. All right, NaF, what do you get when you put that into water? You get a Na plus, and what else? F minus. Okay, perfect. All right, let's work backwards this time. So F minus, is that going to be an acid or a base or neutral? Yeah, so let's undo the conjugate. F minus is the conjugate of what? HF. HF is a what? Weak acid. So if HF is a weak acid, that makes F minus a weak base. Perfect. All right, so F minus is a weak base. All right, now let's look at sodium plus. All right, sodium plus, I'm just going to straight up tell you, is pH neutral. It's pH 7. And the reason is because it is the conjugate of sodium hydroxide. Sodium hydroxide. Sodium hydroxide is a what kind of base? Strong base. So that would make sodium plus a pH neutral salt. There. All right, so if you put something that's pH neutral and something that's basic into water, what are we going to find? That NaF is basic. Perfect. All right. Right. And so remember, so sodium is part of our group 1A elements, and if you go back to this slide of common pH neutral cations and anions, sodium plus, potassium plus, calcium plus, all of these are conjugates of strong things, so they are pH neutral salts. Okay, KBr. K plus, what is that? It's going to be neutral. Why is it neutral? Because it's group 1A, yes. So it comes from KOH, so it is pH neutral. What about bromide? Is that going to be acidic, basic, or neutral? That is going to be neutral. And so the reason is Br minus is the conjugate of what? HBr, and HBr is a what? It's a strong acid, and so conjugates of strong things are nothing. Conjugates of weak things are also weak bases. All right? All right, so you put KBr in water. What do you think is going to happen? Is the pH going to change? Nope, it's going to be a pH neutral salt. And KBr is a pH neutral salt. All right, because both of the cations and anions are neutral. All right, next. Sodium plus. Good, I heard it, it's neutral. You'll be seeing those a lot. K plus, Na plus, calcium plus, strontium 2 plus. All of those are pH neutral because they are group 1A or 2A. But the other one is carbonate. What do we think that is? Is that acidic, basic, or neutral? What do we think? It is the conjugate of, you can think of carbonic acid. Carbonic acid is what kind of acid? It's a weak acid. So that makes carbonate a weak base. Yes, all right. So if carbonate is a weak base, sodium is neutral, this entire salt, if you put it into water, should be basic. Yes, it should be basic. All right, let's keep going with these conjugates. The answers are in the corner. So acidic, basic, neutral, basic. All right, next one. KCN. K plus is what? Neutral. We've seen that already. Cn minus is going to be what? It's a weak base. Yes, because HCN is a weak acid. It's not one of our 7. All right, so its conjugate's going to be a weak base. So KCN, you put that in water, and what will the solution do? It will become basic. Perfect. All right, aluminum chloride. So if we split this up, we get aluminum 3 plus and chloride minus. So let's do the easy one first. Chloride minus, is that going to be acidic, basic, or neutral? Neutral. Why is chloride minus neutral? Because it comes from HCl, which is a strong acid. All right, what about aluminum 3 plus? What do we think? Is it acidic, basic, or neutral? It is acidic. Yes, it is acidic because what was the last slide we talked about? Lewis acid. So aluminum 3 plus is a Lewis acid. It is highly charged and can accept protons from the water that's all around that solution. So Al3 plus is acidic, so this entire solution will be acidic because of the aluminum. All right, let's keep going. Ki. So we get K plus, I plus, or sorry, minus. K plus is what? Neutral, yep, because it's group 1A. I minus is neutral because HI is an acid, but it's what kind of acid? Strong acid, so that makes I minus a nothing, a neutral salt. So Ki, you put that in water. What's the water gonna do? Acidic, basic, or neutral? It's going to be, what do we think? Anyone. It's going to be neutral, thank you. I get stuck in these boot loops until someone says something. So if you want to keep moving along, you got to say something. All right, so in all of these examples, it's been like one thing was either acidic or basic, and the other thing was neutral. And that allowed us to figure out whether the overall salt was acidic, basic, or neutral. Basically, the neutral thing never contributed to whether it was acidic or basic. So let's do this harder one. Ammonium fluoride. Ammonium fluoride is a what? Is acid, base, or nothing? It is a acid, right? Because it is the conjugate of ammonia. All right, so ammonium, NH4 plus, and F minus. NH4 plus is a weak acid because it's the conjugate of ammonia, the weak base. What about fluoride? What is that? It is a weak base, yeah, because it is the conjugate of HF, which is a weak acid. So for this one, is this solution going to be overall acidic or basic? I don't know, right? You have something that's an acid and something that's a base, and usually bases neutralize one another, right? And so you might think, oh, this is pH neutral because they neutralize one another. But here's the thing. The strength of the weak acid and weak bases differ because of the K values, right? These substances have different Ka and Kb values. So in order to answer this question, this one is harder, and I have to give you more information to answer it, is I give you Ka and Kb values here. So we need to figure out which substance is stronger. Is it the weak acid that's stronger? If it is, then the overall solution is acidic. But if the base is stronger, if the weak base is stronger, F minus, then the overall solution is basic. So how can we use these Ka and Kb values to answer this question? All right, so I have ammonium and I have fluoride, but I give you the Ka of HF. And I give you the Kb of ammonia. Did I put HF into water? No. What am I looking at? I'm looking at its conjugate. So should I be looking at the Ka value? No, I need to be looking at what value instead? The Kb value, yeah. So since I'm working with F minus instead, we actually want to look at the Kb value. How do we get the Kb value? Recognize that Kw equals Ka times Kb. So if I already know the Ka value for the acid, I know what the Kb value is for the conjugate base. So I'm just going to estimate this because we're just trying to figure out which one's stronger, right? If HF has a Ka of times 10 to the negative 4, all right? So I'm just getting rid of the coefficient. Just look at the exponent here. What would the Kb be of F minus? Remember what Kw is, it's 1 times 10 to the negative 14. So those exponents have to add up to negative 14. So the Kb value for F minus is to the negative 10. All right, I'm just estimating. You can actually calculate the number, but we just need to look at magnitudes to answer this question. Yeah, all right. All right, so ammonia, I give you the Kb of ammonia, but is that what I put into water? Nope, I put its conjugate acid into water. So what K value should I be looking at? I should be looking at Ka. But how do I get the Ka of ammonia? I have to use the Kb value that's given. So can you tell me the appropriate magnitude of the Ka for ammonium? It's going to be 10 to the negative what? 10 to the negative 9. all right, because the KB is to the -5. All right, so these are the two values that we need to compare. The KB of F minus and the Ka of ammonium. So now, can you tell me which thing wins? Is the weak acid stronger or is the weak base stronger? Just based upon the K values. Which K value is bigger? It would be the Ka value. The Ka value is bigger. All right, it is bigger. All right, so that means that NH4 wins in this case. It is the stronger acid of the pair, and so this will be an overall acidic thing. All right, okay, so how do we feel about that? Okay, do you want to do more? I'll do the demo now. I guess I'll just do the demo. All right, and we'll see. Okay, so let me just, I have all the compounds down here. And so we can do the same thing again. Let's predict. Is the salt, when I put it into water, is it going to be acidic, basic, or neutral? So let's remind ourselves. So here's a bunch of just pure waters with indicator in it. And so just to remind you what things look like when it's acidic, basic, or neutral, here is HCl. I put HCl into water, and what is HCl? It's acidic, so the solution should turn acidic. So let's just remind ourselves. Boop, 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 boop. There we go. That's what acidic looks like. All right, so it turns orange when it's acidic. And then sodium hydroxide is a base, so it should turn the water basic. All right, so let's just reference ourselves because we're going to add a bunch of salts to the water, and we will predict, see if our predictions are correct, all right? Whether the solution should turn acidic, basic, or neutral. And then here's the neutral reference. So here is acidic, here is neutral, and here is basic. All right, so which one are we doing first? We're doing sodium chloride. So what do we think? Sodium is what kind of salt? Is it acidic, basic, or neutral? Neutral. What about chloride? Chloride. Neutral, yeah. So the overall salt will be neutral. Perfect. So here's some sodium chloride. So what color should the water turn? It should just stay the same. So here's sodium chloride. There we go. That's NaCl. Boom. Didn't do anything. All right, let's do the next one. Ammonium nitrate. Here we go. All right, is anything in this formula already neutral? NO3 is already neutral, and the reason is because HNO3 is what kind of acid? Strong acid, and so that makes nitrate neutral, or nothing, whatever, nothing, all right? That nitric acid is so strong that its conjugate does nothing. It's neither an acid or a base. What about ammonium? I've shown this one a lot now. This one is a weak acid, and again, I'll remind you the reason ammonium is a weak acid is because NH3 is a weak base, so its conjugate must be a weak acid. So you put this into water, what should it do? Become acidic. Yeah, so let's see. All right, so this is ammonium nitrate. So which color should it turn? All right, let's see. Ammonium nitrate. Boop, boop, boop. There we go. That's ammonium nitrate, acidic. And what's the part that's making it acidic? What part? The ammonium. That's the cation. Perfect. All right, there's ammonium nitrate. Next one, silver nitrate. Silver nitrate. Is something in here neutral that we can ignore? Nitrate, yes, that one, just ignore that one. Okay, but what about silver? So this is silver plus. This is, yeah, I heard it. It's a Lewis acid. I think. I hope so. Yeah, it's a Lewis acid. So silver plus is a Lewis acid. It's a metal that's not in groups 1 or 2, so it's going to act like a Lewis acid. So what should happen when I put this into water? It should become acidic because of the Lewis acid, because of the silver. Okay, I have to add a lot of, okay, it kind of turned orange, right? It like sort of turned orange. It doesn't dissolve very well. Let's add more. It's kind of turning orange, right? So it's not as acidic as the ammonium, but it is in fact turning a little bit orange. Okay, next one, calcium nitrate. Is there one we can ignore? It's the nitrate. All right, nitrate, that is pH neutral. What about calcium? It is a group what metal? 2A, so it's going to be neutral as well, yes. Because calcium hydroxide is a strong base, so calcium 2+ is going to be a neutral salt. All right, so let's look at calcium nitrate. What should happen? Nothing. Oops. So I'll put a lot in. I'll prove to you that this is pH neutral. See, looks just like NaCl. Didn't change pH at all. All right, next one, aluminum chloride. What do we think? Aluminum chloride, yes, it's an acid. Why is it an acid? It's the aluminum 3+ is acidic. It is a Lewis acid. Chloride, on the other hand, this is pH neutral because it comes from HCl. So let's keep going. All right, aluminum chloride. So what color should it turn? Orange. Man, we need to get some bases up in here. Boom. Ooh, that one's bright. Do you agree that that's acidic? Yes. And what made it acidic? The aluminum 3+, that it's taking the protons. It is taking protons from the water molecules, making the solution more acidic. Okay, what's next? NaF. Is there one we can ignore? One of the ions we can ignore. Sodium. Yep, the sodium is what? pH neutral because it comes from sodium hydroxide. That's a strong base. But what about fluoride? That's going to be basic, yes, because it comes from HF, which is a weak acid. So finally, one that's different. Okay, what should happen? It should turn basic. Hopefully, turn basic. How much do I need to add? I don't know. Ooh. Okay, it turned greener. How much do I need to add? There we go. Yeah, that's different, right? That's different. So do you agree that that definitely is closer to blue than it is orange? Yes, this is basic. All right. Next one, sodium carbonate. What do we see? I heard it. It's going to be basic. What component is making it basic? The carbonate is making it basic because that is the weak base of the conjugate base of carbonic acid, which is a weak acid. So carbonate is a weak base. But sodium plus is pH neutral. You'll see these pH neutral ones come up all the time, all right? All right, so where's the last one? Sodium carbonate, here we go. Carbonate, so what should this solution turn? Basic. So let's see, how much do I need to add? We'll add 2 big scoops. Whew. Is that basic? Heck yeah. All right, so that's what we mean when our acids, acidic, basic, or neutral when you dissolve them in water, we inspect the conjugates that are produced, because what you're looking at are conjugates, and we have to be really aware of what things are acidic, basic, acidic, basic. Those things come from weak acids and weak bases. All right, do we feel better about that? Yes? Okay. And so in all of these examples, one thing was neutral, and so we were able to identify whether the solution was acidic or basic based upon just the presence of a weak conjugate acid or base. But if both things are an acid or base, you actually have to compare the Ka and Kb values. All right, so, let's move on then. All right, that's definitely a common exam question, one that's definitely like multiple parts. That would be really good with a pull-down menu question, right? It's like we just give you 3 salts and it's a pull-down menu. Is it acidic, basic, or neutral when you dissolve it in water? So that's a very common exam question. All right, okay, so let's keep thinking about salts and how Kas and Kbs are related. So in this last question where I had an example where both a weak acid and a weak base were present, we had to compare the Ka values and Kb values, but we needed to make sure that we were comparing the right ones. So let's look at carbonic acid. Carbonic acid is a diprotic acid, H2CO3. Each proton comes off one at a time, so each proton has a different Ka value. So let's write the equation for Ka1 and Ka2. So Ka1 is carbonic acid acting as an acid, but we only take off one proton. So when one proton comes off, what's left over? HCO3 minus, all right? So the second Ka value, so Ka2, what's my reactant in Ka2? Is it carbonic acid? Is it H2CO3? Is that my product in Ka2? Nope, it's going to be, oh, we already took off one proton already, so it's the product in the previous one is now our reactant in the second Ka value. So here we've already taken off that proton, and now we take off that second one. That is what Ka2 is. You take off the second proton after you've already taken off the first. So there we go, and then what's our product in Ka2? Is CO3 2 minus. All right, and each of these have Ka values. So this is Ka, I'm just going to estimate this. I'm going to say that it's 1 times 10 to the negative 7, about. And then Ka2 is about 1 times 10 to the negative 11. So can you tell me which proton is more acidic, the first one or the second one? Which one? And how did you get it? Based upon the Ka values, which proton's more acidic? The first one. Why is it the first one is more acidic? Bigger. Ka is bigger in the first one. Perfect. All right. So carbonic acid can act as an acid, but we already said carbonate, CO3 minus, this guy. Is this an acid? Nope, that is a base. And so what equations do we use to describe bases? Not Ka, but Kb. So we can write the Kb expression for carbonate acting as a base. So let's do that. So Kb1 is where we start with carbonate. And remember, Kb expressions, they're always weirder. Okay, I think I mentioned in my review that in undergrad, for a long time, I thought Kas and Kbs were reverse reactions of one another. They're not, all right? Because you might want to think, oh, carbonate acting as a base is just this reaction in reverse. It's not. Carbonate, when this acts as a base, has to produce hydroxide ion. So in order to do that, I need to add water to this reaction. And this is the Kb expression where carbonate, you can just think of this as base, right? Grabs a proton from water, so you get the conjugate acid, so HCO3 minus, and then what's left over? Hydroxide. That is a Kb expression. See how I produce hydroxide here? All right? And so this is Kb, all right? Kb1, sorry, Kb1. And these are Ka1 and Ka2. All right, so what do you think the reactant is in Kb2? Is it carbonate? Nope, it's going to be bicarbonate, the one with that already has a proton on it already. So we're going to take HCO3 minus, add water. It's going to grab and accept a proton from water, so we get H2CO3. The neutral, so we're getting the full acid back plus hydroxide, and that is balanced. So this is Kb2. Kb2. All right, so in this table, I gave you Ka values, but I didn't give you Kb values, but did I have to? So we're going to use the relationship here, Kw equals Ka times Kb, but we have to be careful, because we need to understand which Ka do we use to calculate Kb. All right, so we got to be careful here. We can't just take any of them, because I think the next thing is calculate the values of Kb1 and Kb2. So I understand that Kb1 is going to be Kw over a Ka value, but which one is it going to be? Is it going to be Ka1 or do I divide by Ka2? This is how we decide. Look at your products and reactants in Kb1. We have carbonate and bicarbonate. Which Ka value, or Ka reaction should we use to relate to this reaction? Ka1 or 2? Ka2. Why 2? Because that's the reaction that has the same acid-base conjugate pair. So Kb1 is actually equal to Kw over Ka2 because that is the reaction that has carbonate and bicarbonate in it. All right? So we did not divide by Ka1 because those are the wrong acid-base pairs. Right? So if we estimate Kb1, what is it going to be about? 1 times 10 to the negative 3. Right? The values don't really matter. Okay? You can put the coefficients and actually calculate it, but let's just get magnitudes. All right. So, therefore, by process of elimination, which Ka value are we going to use to calculate Kb2? Is it going to be Ka2 again? Nope, it's going to be Ka1 because again, if you look at the products and reactants, we have the diprotic acid part and then the monoprotic, and that is what Ka1 also has in its reaction. It's just flipped. So we see here Kb2 is equal to Kw over Ka1. And so let's estimate what is Kb2. 10 to the negative 7. All right, it's about 10 to the negative 7. And again, I'm just looking at the exponents and thinking, how do they add up to negative 14? All right, so which one is the stronger base? Carbonate anion or bicarbonate? What's the better base? It's going to be carbonate. All right, this one's the better base because its Kb value is larger. All right, so let's put this all together. All right, so we got Ka values, we got Kb values. Now, using this same information, tell me, if we put bicarbonate into water, is this going to be acidic, basic, or neutral? What do we think? So when we did salts, right, we split them up. We have sodium plus and bicarbonate. All right, so sodium plus is pH what? Neutral. So can we ignore it? Yes, we can ignore it. Now we need to decide, is bicarbonate acidic, basic, or neutral? It's not obvious, all right, because can bicarbonate gain a proton? Can it accept a proton and act like a base? Yep, there's a spot for it. Can it donate a proton as well? Yep, so we need to decide which one does it do. So we have to compare Kas to Kb values, but we need to make sure that we compare the right ones because we calculated 2 sets of them, right? So this is how I go about it. So I recognize that bicarbonate is part of the carbonic acid system where we take off protons one at a time. So H2A, when that acts as an acid, makes HA minus. A minus is, or A is just carbonate. When HA minus acts as an acid, what do you make? A2 minus, all right? So these reactions are the subsequent Ka values. So in this direction, I have Ka1, which is about 10 to the negative 7, which is given here in this reaction, all right? Then Ka2 is given, it's about 10 to the negative 11. Right, so that's the substance acting as an acid, versus in the other direction, if we think about this. A2 minus can act as a base. HA minus can also act like a base. So in the red direction, the backwards direction, we're moving through the base form. So we're going to put those Kb values there. All right. So this first Kb value, going from A2 minus to HA minus, is which Kb value? Look back at your previous work. Is it Kb1 or Kb2? This is Kb1, yes. Because A2 minus becomes HA minus, it's right here, right there, all right? Carbonate goes to bicarbonate. So that means that the second step here is going to be Kb2. And we got values for that as well, didn't we? Kb1 is 1 times 10 to the negative 3, And then what do we say? Kb2 is 1 times 10 to the negative 7. There we go. So, why did I do this? See, this question would be easier if I asked you, you put H2A in water, what does it become? Acidic, basic, or neutral? What would you tell me? Acidic, it's an acid. But you put A2 minus into water, what does it become? Basic, because it's a base. But it's a little bit iffy for HA minus because can it act as an acid and like a base? Yeah, so what K values do we want to compare? Do we want to compare Ka1? No, Ka1 describes H2A acting as an acid. What Ka value describes HA minus acting as an acid? It's actually Ka2. So this is the value that we want to compare. Now tell me, which Kb value describes HA minus acting as a base? Is it Kb1 or Kb2? Kb2. So these are the two numbers that we want to compare to one another. This describes HA minus acting as an acid or base. And the reason I'm doing that is because what are we putting into water? We are putting HA minus into water. And so we need to think, is it going to act more like an acid or more like a base? So what do you think? It's going to be basic. Why is it basic? Because Kb2 is larger than Ka1. Or sorry, Ka2. Ka2. All right, so this number is larger. So HA minus is more likely to act as a base. That's going to push the reaction in this direction. It's going to act like a base. Because what makes this question harder is that there's two Ka values. There's two Kb values. So which ones do you compare? And so this is the strategy that we want to use. All right. So that's for a polyprotic acid. I recognize that that is a lot. These ones are a lot harder. Okay. How do we feel about that? Yeah. Yes? What do you think if they're equal to one another? It would be neutral, yeah. If it's the same acidity and the same basicity, then they cancel each other out. Kind of like a strong acid, HCl, plus a strong base, sodium hydroxide. Those two things, a strong acid and a strong base with the same like relative strengths, when you mix them, you get sodium chloride, which is a pH neutral salt. So if both of these values were equal to one another, yes, then it would be neutral. Good. All right, so let's finish off these slides. Okay, so let's talk about structure and acidity. So why are some things strong acids? Why are some things weak acids? It all has to do about the stability of the conjugate that is made, all right? Where we can think about this in terms of free energy as well, all right? If this is a chemical equilibrium, which it is, this is HA. If this was back in chapter, I don't know, 5, and I asked you, what is more present at equilibrium? Products or reactants? Products, right? Because it's the low energy point. That's where like everything starts to accumulate, is the low energy point. So if A minus is highly present at equilibrium, this makes that acid so the A minus is the conjugate base, but it makes HA a very strong acid because this reaction ionizes, it moves in the forward direction a lot. And so when A minus is stable, when it's a really stable anion, and there's a way we can look at stability of anions, typically the acid HA is really, really strong, all right? When its conjugate is really, really stable. That's how we have really acidic things. This is a very important concept in organic chemistry, so keep this in your back pocket for organic when you predict chemical reactions, chemical reactivity. We don't just pop off whatever H+ we want to initiate a chemical reaction. We usually start off with the most acidic proton. So being able to identify what is my most acidic proton in a acid or in a substance is really important, right? A proton on an acid is very acidic, meaning very easily donated if the conjugate is very stable, all right? So when we think about stability and how acidic something is, again, if the conjugate is really stable, typically that thing is a very good acid. So meaning we have to take off one of those protons and inspect what's left over. So when we look at, like, let's say the binary acid sequence, like HF, HCl, HBr, HI, are all of those strong acids? No, only one of them is a weak acid. Which one's a weak acid? HF. All right, so one of the reasons HF is such a weak acid, it's not part of the strong acid series, is due to bond strength. If you just look at these bonds, HF, HCl, HBr, HI, when we go down a group, atoms get what? They get, boom, bigger. They get bigger. So as our bond length gets longer, typically, what was the trend? Long bonds, are those strong or weak bonds? Weak. Versus nice short bonds, those are strong bonds. So if you just look at these bond lengths, which one is the strongest? HF. HF is the strongest. So is it very likely that that proton's going to pop off if it's a strong bond? No. And so that's why HF is a weak acid. Versus HCl, HBr, HI, bond length gets longer, it gets weaker, and so these protons much more likely to donate a proton because the bond is weaker. Versus HF has a very strong bond, so it's not likely that it's going to, so strong bond, I should say, pop off that H+. All right? So that describes why, like back in Chem 1210, when people are like, well, why is HF weak and HCl is strong? And we just kind of say, okay, ignore that, just memorize it. This is why HF is a weak acid. It's because that HF bond is really, really strong. And so only some of those protons get donated when you put it into water, but some of them stick together because that bond strength is so strong. Okay, so that's one way to think about acidity based upon structure. We can look at bond strength of that proton. We can also look at the structure of the conjugate base. So conjugate bases, all right, if we have HA, what's the generic conjugate base of HA? A minus. A minus is a, what, cation, anion? It's an anion. So negative charges typically aren't super stable unless we can stabilize that negative charge somehow, right? Charges are typically reactive. So if we're able to spread out that negative charge in a molecule, we can actually stabilize that conjugate base, making the acid a lot stronger. So here are the trends. Okay, so let's remember why, let's remember these strong acids. Part of our strong acids were perchloric acid, chloric acid, all right? Those are strong acids, but what about chlorous acid and hypochlorous acid? What kind of acids are those? Those are weak. That's a weak acid, but both of these are strong acids. What's the trend here? Look, I'm taking off oxygens. When there's a lot of oxygens on my formula, it seems to be that it's a strong acid. But as I take them off and there's less oxygens, they become weak acids. And the reason is that that oxygen, the presence of oxygen in a formula actually stabilizes your conjugate base, making it a more acidic acid. So the idea here is the conjugate base is negatively charged. Oxygen. What kind of electronegativity does oxygen have? Is it high or low? It's pretty high. It's part of the high five, I like to call. All right? Oxygen likes electrons. So if you have an anion that has a lot of electrons on it, that oxygen can accommodate that negative charge on the conjugate base, making it more stable. So here you see, all right, hypochlorous acid, only one oxygen to stabilize that negative charge. That's not very good. Here, chlorous acid, now you have two oxygens to spread around that negative charge. That's more stable, but still a weak acid. But once we get to a point where, hey, now you have three oxygens that you can spread around that negative charge. Spread around, what does that sound like? Resonance. It's because it is resonance, right? Resonance stabilizes things, and you can move around that negative charge, making it the conjugate base more stable, versus perchloric acid has four oxygens. And so again, you can stabilize that negative charge across four oxygens. That's how you increase your acidity here. Right? So the trend is here is for many acids, more oxygens typically means more acidic. And this is, this is the reason, because oxygens stabilize your conjugate base, right? So that's the trend. Another trend is if your central atom is very electronegative already, all right? If your central acid is very electronegative, electronegativity means ability to accept electrons or attract electrons to itself, then you also have a very acidic acid. So if your central atom is high in electronegativity, it's also more acidic. More acidic. All right, so if like, for example, it was like Cl versus, like if I did ClO3, HCl3 versus HBrO3. HClO3 is going to be more acidic here because chlorine is more electronegative than bromine, all right? Versus if I wanted to compare HiO3 is going to be what? More or less acidic than these two guys. It's going to be even less acidic because iodine is even less electronegative than those things, all right? So more electronegativity on your conjugate base. You can stabilize that negative charge, making a more acidic acid. And this is, again, a very important skill in organic chemistry. I'm probably doing a poor job of it, but they'll teach you it better next year. Okay, so I mentioned oxygens stabilize that negative charge on the conjugate base, making it more acidic. That sounds a lot like resonance because I'm smearing around that negative charge across many oxygens. So resonance is another example of how we can stabilize conjugate bases and make it more acidic, all right? So in all of these examples, I give you the acid form, but what we want to do is inspect the conjugate and think if the conjugate is stable, if the conjugate can participate in resonance, then that makes a very stable anion, and typically that acid is very acidic. So here's an example, acetic acid. If you take a proton off of acetic acid, so take off the proton, but what's left is a negative charge on that oxygen that we broke the hydrogen bond with, look at acetic acid. All right, we got a double bond and we got a single bond. Can this participate in resonance? Do you remember that from Chem 1210? Yes, this can participate in resonance. That this double bond can either be here or it could be over here. It doesn't matter, right? So acetic acid is very acidic because it can participate in resonance. Once you make that conjugate base, it can participate in resonance, so that proton is very likely to pop off. Or let's look at formic acid. All right, formic acid, you take off that proton, you're left with a negative charge on that oxygen. Can this molecule participate in resonance? Yes, it can, for the same reason. There's a double bond here, or you could put the double bond there. So again, this can participate in resonance also. So we see a very high Ka value. This is highly acidic as well. This is very acidic. Okay, because these conjugates can participate in resonance. All right, what about benzoic acid? When you make the conjugate base, can this participate in resonance too? Yes, they all, for the same reason. They all have a similar looking group where we have a carbon, 2 oxygens, and one of them's double bonded. And so we see benzoic acid is also very acidic as well because of that ability to do resonance. All right, so let's look at an example where it can't do resonance. All right, so ethanol. Here's the proton. It's right here. Okay, so let's pop that off. Let's rip that off. All right, and think about what's left over. We have a negative charge on an oxygen. But can this molecule undergo resonance once I make the anion? No, it can't. That negative charge is stuck there. And so if you have a localized negative charge, that is unstable. This is very unstable. All right, this is unstable. Okay, cannot do resonance. Cannot do resonance. So look at that Ka value. Is ethanol acidic? That Ka value is really small. It's super, super, super small. All right? So ethanol is not acidic at all because it cannot undergo resonance when we take off that proton. All right? So protons are more likely to pop off and act like an acid if the conjugate base that's left behind is really stable on its own. All right, so ethanol is not acidic at all because it cannot do resonance. All of these three other examples have that CO2 minus group on it. We call this like a carbonate group that can participate in resonance and typically adds to the acidity of these acids. You see that these Ka values are fairly large. 10 to the -4, -5, those are big numbers versus 10 to the -16 is very low. All right, so let's do one last slide and then we'll move on to review for the midterm, but we'll just put it all together and see if we can't choose which acid is more acidic of these different pairs. So remember the ideas here. If you can stabilize that negative charge of your conjugate base, then things are going to be more acidic. So what do we think? HBrO2 or O3? Which one is more acidic? How about I just say column A or column B? What do we think? A or B? B, why? More oxygen. So more oxygen stabilize that negative charge. Okay. HiO2 or HBrO2? What do we think? A or B? B, yes. Why? Bromine is more electronegative than iodine. Remember, fluorine is the most electronegative, and then it decreases going towards cesium. Right? So bromine's more electronegative than iodine because it's iodine's lower on the periodic table. Right? And so the more electronegative central atom is going to stabilize that negative charge more. Notice how I make the number of oxygens the same because that's the only way we could ask it. I couldn't change both the number of oxygens and the central atom at the same time. That's just evil. I can't ask that. I just have to change one variable at a time. All right, which one's more acidic? FeCl2 or FeCl3? This one's tricky. This one's tricky. Okay, remember when we did the demos, right? Iron cation is what kind of acid? It's a Lewis acid. So when you dissolve iron Cl2 into water, what kind of iron do you get? Iron 2+. Versus the other one is what? Iron 3+. So which one is more acidic? The 3+. If this is a Lewis acid, right? If this is a Lewis acid, the trends were charges affect acidity. More positive charge will attract electrons more, right? So Lewis acids talk about, accepting electrons. A 3+ is more, has more charge there, more attraction. So I guess more Lewis acid, I guess. Is that what I want to say? Okay. Ammonia or ammonium? Cation, which one's more acidic? Don't think about it too hard. Ammonium, how do you know ammonium is more acidic? It's an acid versus ammonia is a base, yes. Hydroxide or water? What do we think? Which one's more acidic? Water, yes. And here's another way we can think about it. Let's go back to the ammonia example. If these act as acids, think about what's created, the conjugate base. You rip off a proton off of ammonia and you get NH2-. You rip a proton off of ammonia and you get NH3 neutral. Which of these is more stable, the neutral thing or the negative thing? It's going to be the neutral thing. So same idea here. You rip off a proton off of hydroxide, and what do you get? O2-. That's not very stable at all. Versus water, you get OH-, which is very common. We use that all the time. And so we see hydroxide is much more stable than O2-. All right, and the last one, A or B, which one is more acidic? A or B? What do we think? This one, A or B? B, why? Because it can participate in resonance, right? You take off this proton versus this proton, all right? You're able to stabilize that negative charge by smearing it around within resonance. Okay, all right, so we got 15 minutes left, so I'll just rewrite the thing. So go.osu.edu 1220 Rev 2 if you want to get the document that I'm going to work through. So we got 15 minutes, but I just got a couple slides on acid-base chemistry. Remember, midterm 2 just covers the table, so like relative acidity and basicity of acids and their conjugates, so no numbers. And we do pH calculations with strong acids and strong bases. But here's the thing. Now you understand the numbers, right? You understand the numbers. You understand that Kw is equal to Ka times Kb. So if you have a really strong acid, Ka is what kind of number? Big. And if these two things, when you multiply them together, have to add up to 10 to the negative 14, if Ka is big, Kb for the conjugate has to be small. Versus if you have a really crappy acid, Ka is what kind of number? Small. So therefore, Kb is big. And then the conjugate base is what kind of acid is a pretty good, or sorry, what kind of base? A pretty good base or a crappy base? It's a good base. So we learned about the numbers, but you're not going to be assessed on the numbers. We just use the table. But it's still the same stuff. All right, so let's do this. Okay, HF is a what? Select all that apply. Is it a strong acid? No. Is it a weak acid? Yes. Is it a Bronsted-Lowry acid? Can it donate a proton? Yeah, there's a proton on it. Is it a Lewis acid? Yes, it is, because what do Lewis acids do? Accept electrons. This proton right here can go ahead and accept electrons. All right, so note here that it's an acid, so it's going to be a Lewis acid and a Bronsted-Lowry acid. It fits within that definition. All right, let's write the Ka for HF real quick. What's the Ka expression for HF? HF goes to what? Oh wait, the Ka expression, sorry. Ka expression, so not the equation. But it comes from the equation. I'll just write the equation anyway. HF goes to H plus F minus its conjugate, so therefore Ka is equal to H plus concentration at equilibrium, F minus at equilibrium over HF at equilibrium. All right, products over reactants, same exact K as before. You just want to make sure you use the right Ka expression. Okay. F minus is a what? Is it a strong base? No, we already talked about this, right? About inspecting salts. Is F minus a weak base? Yes, it is. We looked at it here. We put sodium fluoride in water and we saw it turned it basic. It's a weak base. Is it a Bronsted-Lowry base? What do we think? What do Bronsted-Lowry bases do? They do what to protons? Accept them. Can this F minus accept a proton? Yes, it can, so it is a Bronsted-Lowry base. Is it a Lewis base? Yes, it is, because Lewis bases do what? Donate electrons. Are there any electrons on this fluoride that could maybe be donated? Yeah, there's a butt ton of electrons there. Yeah, so this is definitely going to act like a Lewis base as well. So see how all of the base things except the strong ones are selected here. So Kb for F minus is different, right? When things act as bases, you have to add water as your reactant. Water doesn't end up in the K expression, but you need that water to be there, because what happens is that F minus needs to grab a proton, right? Accept a proton, and it has to come from water in this case, so you make HF, your conjugate acid, back, and then you get hydroxide left over that comes from water, all right? So that's the idea with KBs. You need to have a water molecule present in that expression. KAs are easy. You just take H and A and you split them up. But KB is a little bit trickier because you have to have that water present. So KB for this expression is equal to HF times hydroxide concentration over F minus concentration. Do you put water in here? No, you don't. Not in the K expression, but it's still in the chemical reaction. It's a liquid. Sorry, I'm ignoring states because I'm lazy. All right. Okay. If HA is a strong weak acid, what does that mean? If HA is a strong weak acid, Ka is what kind of number? A big number or a small number? Big number. So that means A minus is a what? Is it a good base, poor base, good acid, or poor acid? What do we think? If HA is a really good acid, A minus is going to be a what? Poor base. Yes, it's never going to be an acid. A minus doesn't have protons. Doesn't have protons. If it's a poor base, what is the Kb of A minus? It is a small number, right? Both of the Ka, Kb, they have to multiply to Kw. All right, let's keep going. B, if B is a really good, strong base, that means its Kb value is what kind of number? It's a big number. It's a large number. HB plus, though, is going to be a what? Good base, good acid, poor acid. It's going to be a poor acid. Yes, poor acid. What will its Ka value be? Small. Good. All right. Okay, let's keep going. All right. If HB plus is a better acid than HA, compare the basicity of B and A minus. B is a blank base than A minus. What do we think? Stronger or weaker? Okay. If HB is a better acid, let's just think about that. If HB plus is a better acid, that means B is a what kind of base? Bad base or good base? Bad base. Right? B is a bad base. Because we can make that conclusion because we say HB plus is a better acid than HA. Both of these are acids, so therefore B is a what? Weaker or stronger base than A minus? It's going to be a weaker base than A minus. Those are the conclusions we can make. All right. Okay, keep going. All right, given this table, what's a better acid? This proton or this proton on ammonium? Did I give you acids? Nope. Can we not, answer this then? Nope, you can. Because what's the idea here? These are acids. So if HPO4 2 minus acts as an acid, what do you get? You get H plus and what? PO4 3 minus. PO4 3 minus is a base, a conjugate base. It's conjugate base. What do you get when ammonium acts as an acid? You get H plus, and then what's left over? NH3. Are these two things on the graph that I gave you? Yep, they are. So can we answer this question? Yes, if we want the better acid, what do we actually want to look for in comparing the conjugate bases? We want to look for the worse base, right? So let's locate where these are on the table. We have ammonia, there it is, and where's PO4? Right there. So which one's the poorer base? NH3. So then which one's the better acid? Ammonia. Sorry, ammonium. Yes, this one is the better acid because NH3 is the worse base. All right. Okay. Keep going. Do we like concepts or do you like math? Math. Okay, so let's do math. Or not really. I think none of this actually has, I don't have any calculations on here. Nothing that you can't just do in your head, all right? Okay, so we're at 25 degrees. What's the significance of that? That means, are we allowed to do pH plus POH equals 14? Are we allowed to do that? Yes, we are. And the reason we can do this, 14, I didn't just pull that number out of my butt. Where did 14 come from? It's actually PKW. Take KW, 1 times 10 to the negative 14, take the negative log of it, and what do you get? You get 14, all right? So really, pH plus POH equals 14 is you take the KW expression and you negative log both sides. That's what it is. Okay, so if we have a solution that's pH 8, what is this solution? Acidic or basic? Basic, perfect. What does that mean? Is H3O plus greater? Is it less, or is it equal to hydroxide? Less, yes, that is what basic means. Okay, let's keep going. A solution has a pOH of 8. What is this solution, acidic or basic? It's not basic. We always reference ourselves to pH. So if I give you pOH, what will be best for you is if you just convert that into a pH so we can reference it within our scale. Small pH numbers, acidic, larger ones, basic. So if pOH is 8, what is pH? 6? Yeah, 6. So that means this solution is acidic. And so what does that mean about this solution? What's more present? Acid. So the first one. That's what acidic means, right? Okay, because what if I told you you had a solution at 100 degrees Celsius and I told you that the hydroxide concentration at equilibrium was greater than the H3O plus concentration at equilibrium? Is this solution acidic, basic, or neutral? Or can you not figure it out because I don't know concentrations? No, you can, because what's the definition of basic? When hydroxide is more present. So this solution, even if we're at any temperature, doesn't matter. If hydroxide is more present, then that's a basic solution. Okay, how much more? Okay, last one. What is the pH of all these things? And of course, we're at 25 degrees Celsius. All right, I try to make these numbers easy. So you need to ask yourself, is it an acid or a base? But you're only assessed on strong acid, strong base calculations. So we just have to determine how much H plus or how much hydroxide is present in this solution to get the pH. So if I have 0.1 molarity HCl, how much H plus do I have in this solution? Also 0.1 molarity, because this is a strong acid. HCl fully ionizes. So what is the pH value? Maybe put it in your calculator, but I just recognize how many times do you move that decimal place? Once. So this is pH of 1. This has a pH of 1. But put it in your calculator. All right, what if we have a 0.1 molarity HBr solution? What's the pH? Do you need to put that in your calculator? No, because HBr is also a strong acid. So what we're going to see is H plus also equal to 0.1 molarity. So this also has a pH of 1. What about the next one? What is the pH? 1. Why is the pH 1? It is also a strong acid. Perfect. Oh no, now I changed it. Sodium hydroxide, what's that? That's a base. So we can't get hydroxide, H plus concentration directly. We're going to do this a little bit differently. Sodium hydroxide is a strong electrolyte, so we can make an assumption that the hydroxide concentration in this solution is 0.1 molarity. So how would we calculate pH? We want to calculate pOH first. So what is pOH? 1. So does that mean this solution's acidic? Nope, because what do you got to do? You got to convert to pH, so what's the pH? 13. This is all at 25 degrees Celsius. Okay, perfect. What about 0.1 molarity KOH? What is the pH? 13 again. It is 13 again, because the concentration of hydroxide is the exact same. Sodium hydroxide, potassium hydroxide, both of them are strong bases. All right, does that mean 0.1 molarity calcium hydroxide also is a pH of 13? No, it's not. It's not, because what is the concentration of hydroxide in this solution? It is not 0.1, it's actually 0.2 molarity. So our pOH is going to be a little bit different. I don't know what it is. I didn't calculate it. But without even doing a calculation, is it going to be more or less basic than 13? It's going to be more basic because there's more hydroxide. So we can just go ahead and calculate that, 0.2. So this pOH is 0.7. So that means that the pH is equal to 13.3. So yes, a little bit more basic. All right, that's it. Good luck, everybody. Good luck. No homework due on Monday.